We are first introduced to models of what an atom might look like. We are usually shown atoms as consisting of negatively charged electrons orbiting a nucleus that has positively charged protons. This model, which seems eerily analogous to the planetary model of the solar system, is called the Bohr model. The Bohr model doesn't give us a full picture or model of the atom. However, there is some information from the Bohr model that can be used to describe a more accurate model or representation of the atom. Firstly, there is a central nucleus. Secondly, electrons can be found at certain distances around the nucleus. But the most useful insight from the Bohr model is that electrons can be found at discrete energy levels, and that the higher the energy level of the electron is, the further away from the nucleus it will be found. This energy level is often represented by the letter n, where n is one of the quantum numbers. Quantum numbers will help us to create a more accurate model of the atom. The quantum number represented by n is called the principal quantum number, and it refers to the energy level of the electron and the distance at which it is most probable to find an electron. The next quantum number is represented by the letter L, and it is the angular momentum number. The angular momentum number L describes the shape of an orbital compared to the Bohr model, which had circular orbits. The orbitals have more complicated shapes. We can think of orbitals as regions where we have a probability of finding an electron. We will look closer at this idea later in this video. But first, let us paint a clearer comparison. The atom we have been looking at so far is a silicon atom, which is an element that is very important for semiconductor chips and solar panels. The silicon atom has two types of orbitals, which are s orbitals and p orbitals. S orbitals have a spherical shape and correspond to L equals to 0. P orbitals, on the other hand, are very different compared to s orbitals. P orbitals are dumbbell-shaped and correspond to L equal to 1. These dumbbell-shaped orbitals occur in 3 dimensions along 3 different axes. We could think of these orbitals as describing an orientation of an electron's angular momentum along a given axis. So this orientation about a given axis is described by the magnetic quantum number denoted by ml. Since the s orbital has one orientation, it has one magnetic quantum number. And a p orbital has 3 magnetic quantum numbers representing the x direction, the y direction, and the z direction. If we look at the first s orbital of the silicon atom at n equal to 1, there is an electron that we could probably find in this region. It is important to note that the electron will not be moving in such a predictable way, but what is of interest now is that the electron is moving in a particular direction. It has been shown in this way to illustrate that it has an angular momentum in and of itself, or an intrinsic angular momentum. A single full orbital can contain 2 electrons, but these electrons cannot have the same angular momentum. If that was the case, it would mean that electrons have exactly the same quantum numbers, which is impossible according to Paulis' exclusion principle. So the last of the quantum numbers is called the spin quantum number, and it ensures that electrons in the same orbital have different intrinsic angular momentum, and therefore 2 electrons at the same energy level in the same orbital will not have the same quantum numbers. To understand this intrinsic angular momentum called spin, think of the electron as a bipolar magnet with a north pole and a south pole. If this bipolar magnet was shot through a pair of plates with a magnetic field, it would have a tendency to move in different directions based on its orientation as it interacts with the magnetic field. Therefore, spin appears as angular momentum differences caused by differences in magnetic moments. So this would apply to p orbitals as well. An electron is likely to be found in these blue regions. Again, the electron will not be moving so predictably, and there can only be a maximum of 2 electrons in each orbital. If we build up the silicon atom, we get increasingly larger s and p orbitals. These orbitals interact through interference to form covalent bonds. So, what exactly do we mean when we say a region in which we are likely to find an electron? When we say that, we are really talking about probabilities. Similar to throwing a coin in the air, when it lands, we can either get heads or tails. While the coin is in the air, there are 2 possible outcomes with a 50-50 chance of either heads or tails. Similarly, these regions are places where if we looked, we have a chance of finding an electron. If we looked multiple times, we would find the electron in different positions. We can see that even within the s orbitals there are places in which we have no chance of finding an electron. So just as the probability distribution of a coin landing on either heads or tail is given by 50% or 0.5 out of 1, what type of probability distribution is giving us all of these strange shapes? And the answer is that it is the Schrodinger equation which gives us these types of probability outcomes. This is the Schrodinger equation, and it is one of the most important equations in quantum mechanics. Think of it as Newton's laws for subatomic particles. In order to build an intuitive understanding of the Schrodinger equation, let us look at the terms in the equation separately. The first term of interest is the psi term. In this equation, psi represents the wave function, which in simple terms tells us that subatomic particles behave like waves. The r and t in the brackets tell us that this wave function depends on the distance from the nucleus and time. Now we will look at the h bar over m term. This term comes from rearranging the momentum equation, so it really speaks to the momentum of a particle or energy associated with motion, that is kinetic energy. The inverted delta sign is called the Laplacian operator, and it tells us that this movement is three-dimensional with momentum in the x, y, and z directions. The v term represents the potential energy of these particles. The term d over dt makes it a differential equation, and it tells us that this wave function changes over time. So the Schrodinger equation tells us that we are dealing with particles that behave like waves with kinetic energy and potential energy. It also tells us that this wave function changes over time. The h and h bar terms further tell us that there is quantization occurring.